Hello, my name is Parker Webb, and this is the Physics 2212 Lab 3 about circuits. The purpose of this lab is to further understand how voltage and current relate in circuitry and see how charge is stored and ejected from capacitors. Some helpful equations is V equals IR, that the change in V is equal to Q over C, that Q over C minus IR equals 0, that Q over RC plus dQ over dt is also equal to 0, and that delta V is equal to delta V naught times e to the power of negative t over RC. During the first experiment, we utilized 2 voltmeters, 2 different resistors, 2 1.5 voltage batteries, and a wire connecting all the components. After fully connecting the circuitry, measure the current and potential difference along the circuit before and after each resistor, meanwhile recording all of the data. The data for this first experiment sees a regular current of around 0.92 to 0.98 milliamps, a total voltage of around 1.52 volts, the voltage across resistor 1 being about 1.046 volts, and the voltage across resistor 2 being 0.491 volts. Using the current and the separate voltages, we find that resistor 1 was about 100 ohms and that resistor 2 was about 56 ohms. And here we have a graph depicting the change in voltage over time and resistors. In experiment 2, we utilize 2 1.5 voltage batteries, a capacitor, and a light bulb. With the battery and an uncharged capacitor with the light bulb combo, we note the brightness and duration of the light. And then we run the experiment again, but with a fully charged capacitor and a light bulb with no battery. In this combination, we also note the brightness and duration of the light. The data for this experiment showed that with the battery and uncharged capacitor, the light bulb was very bright and lasted for about 19 seconds before fully going out. And with a fully charged capacitor plus a light, we got a somewhat dim light that only lasted for around 9 seconds. Our what if is how fast the capacitor would charge if there were no resistors in the circuit, and a higher voltage would result in a higher rate of charging. However, in a mathematical model, reaching a 100% capacity for a capacitor is impossible, as the graph is asymptotal and that it'll never fully reach 100%. But in real life, we know a full charge at about 95%, which takes around 5 times the resistance times the capacitance.